Hey everyone, my name's Matt. I'm going to do a shortened form of a workshop I've done a couple times at the Game Space called So You Want to Program the Atari 2600. So in this workshop, we're
Sweet
going to use,
chaos. Sorry, Matt. I'm going to interrupt you a couple of times, and I apologize for that ahead of time. But we got another donation for $10, so thank you, Sweet Chaos.
I was trying to think if like the PowerPoint theme I hear was called Sweet Chaos or something. I was like, okay. Um, anyway, so in this little workshop, everyone is able to work along live. Um, we have a online IDE called 8-Bit Workshop, and all of the code is in GitHub. And in fact, foot your mark, if you check the stream channel, I have two links in there that you can paste into Twitch for people to follow along. Also point out this is a survey. I keep things as simple as possible. Once you start doing this for real, if you do it, you spend an awful lot of time hyper optimizing stuff. So most of the ways things are done here are the simplest possible way, not the cleanest way. And also super important, just because of how this 2600 works. It's really easy to make the screen blink. Some of these exercises will make it blink. So if you have any kind of seizure disorder, I would probably recommend not watching this. If you're doing it locally, there's a power button. You can always turn it off, and let me know if it'll be an issue. All right. So for those of you younger than like 100, the Atari 2600 was one of the earliest video game consoles. It was not actually the first. There was the Magnavox Odyssey, the Fairchild, Channel F, and Pong machines. But it was probably the earliest truly successful video game console. And when I say truly successful, so it was released in 77 for $200 in 77 money, which is more now, but still pretty cheap with 9 games. 1980 at least with Space Invaders, had 2 million in sales, 2 billion in revenue. Over the next 2 years, it had almost 10 million in sales, 7 million units of Pac-Man were sold. Then in 1983, in part because of the 2600 others, there was a video game crash that basically knocked out consoles and even home computers for a while. They kept selling the Atari 2600, also called the VCS, until 1992, at which point they'd sold 30 million units. Now, I know by some modern console standards that doesn't seem like a lot, but it was truly like a massive success at the time. So the Atari 2600 is probably one of the most difficult consoles to program ever created, and part of what we're going to do in this little workshop is show why. So it had a MOS 6507 chip, which was basically a cheaper variant of the 6502, which you'll know from such computers as the Apple II, or consoles as the Nintendo Entertainment System, which is a fairly popular one. It only had 128 bytes of RAM. One way to think of that is you could only fit 128 characters in the memory in this. It had a 4 kilobyte ROM. When you have a cartridge-based system like the NES, if I go back, that little slot there, just kind of like an NES, you stick your cart in there. That literally has all the memory. So that's the ROM. It pushed out NTSC, which is a standard TV signal with 128 colors, 60 frames per second. That's right, it does 60 frames per second. Some of our modern consoles can't even always hit 60 frames per second, so it has that. And it was at the incredible resolution of 160 by 192. There's actually a PAL version too, which is at 50 frames per second. And because of that, you can't actually play any of the PAL games on non-PAL Ataris, just because of how it works. And it uses a custom chip. the basic architecture of this is you had your CPU, you had your cartridge, which was the game. You had this thing they called the TIA, which was the custom chip that interfaced it to the television. You had some RAM and timers and your controllers. So it was a really simple system.
Doom runs on anything. RAM
So
be damned.
earlier I said...
Sorry. So we got another donation from Doom Runs on a Pregnancy Test. Thank you so much for that.
I think it's also worth noting how much more powerful a pregnancy test is than an Atari 2600.
Nice segue.
Quite literally. So when we said 128 bytes of RAM, so pretty much any other console or computer in existence since the 2600, including probably that pregnancy test, if it can run Doom. And again, literally. When you draw to it, you have what's called a frame buffer. And that's just a section of memory that's literally mapping the pixels to go to the screen. And if you look at what an 128 byte frame buffer would look like with 256 colors, it looks like this. It's only 8 by 8. And remember earlier I said this was 120 by 196. And RAM was incredibly expensive at the time they did this. And remember, they made it hit this $200 price point. Like adding more RAM, just adding 8K of RAM would have increased the price by $125. It would have doubled the chip. If you double the price of the chip, you'd get... The chip was cheap because it addressed less RAM. And Apple II, which was actually the computer we had growing up, it cost $1,300, which is $5,500 now. So a lot of the reason that the 2600 is so insane is to keep that price point. Okay, so now we're going to jump to the exercise portion of this. So if you want to play along, here's what to do. So go to 8-Bit Workshop in your browser. And now I'm out of my PowerPoint, so I can paste that. So go there. Oh, thank you. Thank you, guys. And then you click on Continue to 8-Bit Workshop IDE. And you'll get to something like this. And this is a completely free and kind of incredible browser-based IDE that lets you make 2600 games, NES games, Pally Astrocade games. I don't even know what those are. Master Systems games, 7800 games, Apple II, ZX Spectrums, Atari systems. You can go and actually use Verilog to make completely custom games. It's a really great tool. Now, if you do get into 2600 or just any of this old console development, there are tool chains you can run out of the browser, which is really what you do. But this is a great start. So the other part of this is for this workshop, in my GitHub over here on MoosePod, we'll also paste this in. I have both general information and then the exercises here. And so every one of these exercises is going to start with one of them. So we're starting on exercise 0. And basically we're just going to copy and paste from here, and then we'll click on raw. And then we'll go to the next thing. So here's what we're going to do. I'm going to copy this text here. Then what you're going to want to do is just paste it into the first thing that opens here. I say the first thing because there is some weird Chrome bug I found earlier where if you try and add a new one, it breaks. So just paste it in. Ignore everything you've seen here. Now what we're going to go down is where it says insert code below this and above this. You're going to type this, LDA pound $80 and star call UBK. And when we do that, you can see over on here on the right, you've just made your 2600 draw a blue background. I know, it's incredibly exciting. But let's walk through what's going on there. For this Buffalo thing, I call it the Bills blue background. I tried to get the color as close as possible to the official Bills blue.
How many colors does the Atari even have access to?
I believe it's 128, and just to so one of the things with the 2600 is almost nothing is simple. So let's actually talk about that colors. That's a great thing. So as is pretty obvious, these two things here affect the color we just saw. So I'm going to change this to 60. Now it kind of goes purple. 50. I don't know, more purple. The color charts actually look like this, where the one you have your two hexadecimal digits, and we'll talk about that in a sec. So we could go to, like, if we want this blue, we could go to AC, and there we get that blue. Okay, so hexadecimal, what the hell am I talking about? So hexadecimal is base 16. And what that means is every digit counts from 0 to 15 except use letters. So it counts like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, G. No G. I got distracted because Clark was posting and it popped up. But what's useful about hexadecimal, and we'll see this in a second, is that it maps directly to binary, because every four digits of a binary number, which, believe it or not, is called a nibble, maps to one hexadecimal. So if I type 00, that maps to the binary value of, I'll pull this over here, 0000000. So here we can see 129 maps to 81 hexadecimal to 1000.
Not just the villain on reboot.
We just got a donation from Hexadecimal, not just the villain on reboot. So double throwbacks.
It is great. It is a useful thing.
Thank you.
And again, I will completely run out of time if we go into hexadecimal. Honestly, all this, the binary hexadecimal, it's not hard. It's like a lot of things, you just have to practice. If you can learn to count to 10, you can learn hexadecimal, you can learn binary. The more you work at it, the easier it gets. Also, hi, Elf Song Tavern's mom. Okay, so what is going on here? So basically, like we said before, frame buffers are too expensive. So we mentioned that the 2600 has a chip called the TIA, and essentially has a bunch of what are called registers in it. And registers are a special kind of memory that are faster to research. So when we say LDA 00, or that's a very boring color. Let's try 70. So when we say LDA 70, that's moving the hexadecimal number to something called the accumulator. The accumulator is this part of the chip that's used to store numbers temporarily. So this puts the hexadecimal 70. I will change it to 10 because I know exactly what it is. So this is the number 16 decimal. This moves the number 16. Well, that is a nice color. This moves 16 to the accumulator. And then when we say sta kalu BK, what that says is put the number that's in the accumulator into the special register that controls the background color of the TV. And so going to my frame rate thing, what's interesting about this, again, this is not like putting the color, this is not filling a series of pixels with this color. It's literally turning on this thing. So the circuitry that outputs the TV is just constantly outputting that background color. So LDA, load to accumulator, STA, store accumulator. And if you have those two things, you've just learned 6.502 assembly language and started programming on the 2600.
So while we were in that, we got another donation from basically all of the hexadecimal characters, and then their message was G G G G G G. You know that G does not exist, so we just move on from there. Thank you very much.
That would be base 17, which I guess you could do, but isn't super useful. Also, Futch, I'm going to rely on you to call time.
You're good right now. We have overflow going in this, and then we've got some fun closing, basically free for all after this. So you are good.
All right. So now we're going to do our next thing. So we're going to go to exercise 1. Copy this code back over here. Now we're back to our black screen. Now we're going to type this. STX call BK dex. Now we see this exciting visual on the right. So what's happening here? Before we do that, I'm going to make one more change here, which is to type sta wasync. And so you see after typing that, it now goes from these kind of broken lines that are cycling to solid lines that are cycling. So before we move to the next thing, so we already know that color bouquet is the background color. STX, well, STA is stored to accumulator. I'll let you in on a secret, which is that there are 2 additional registers called the X and Y. So STX takes the value of the X register, puts it in call BK. DEX stands for decrement X. So every time it hits here, it's taking 1 from X and lowering that number. So essentially this is looping around and changing the background color from the numbers 255 to 0, looping endlessly. Now I made a joke earlier about overflows. Well, so because this is a single byte, which is 8 bits, which is 256 total numbers, every time that we get to 0 in decrement, it moves back to the top, 255, and it just goes and goes and goes and goes. But why are we getting this weird looping pattern? Okay, so remember when I said the Atari 2600 was incredibly difficult to develop on? So what you're looking at here is a diagram of the NTSC picture signal. And the fact that you have to start by understanding how NTSC works to even understand how a 2600 works is why it's hard. So here's what's going on. When you have a TV, and not like a modern TV, not like an LCD, but an old CRT, the way it works is it's taking an electron beam, it's scanning it from one side to the other, it's then moving back to the other side, it's doing that all the way until it hits the bottom, it moves to the top of the TV. And in particular, the way that works is it has 3 lines of what's called vertical sync, which is just so the TV can pick the beam. It has 37 lines of vertical blank. That is, it is not actually drawing. And this is to account for space at the top of the TV. Then you have 192 lines of actual visible picture. Then you have 30 lines of overscan, which is the bottom of the TV, and then it stops again. And when you see this 228 clock counts, what this means is the CPU can do essentially 228 units of things in every line. And here's where it gets nuts. Because of the way that the 2600 draws stuff, your code is running at the same time as the video signal. So here we have these 40 lines at top. So we can use this time to do some work. And here we actually have 22 before it starts drawing. But if we make changes to anything while it's drawing, those changes happen instantly. And essentially the art of programming the 2600 is something that has been called racing the beam, which is you are fiddling with these things live with the timing such that you're done with what you need to do by the time it's finished. And these timings are incredibly, incredibly tight. To understand them, if you look at these numbers here, this is how many cycles these instructions take. So for instance, just this store the background color and decrement, that takes 5 cycles in of itself, which means we're a quarter of a way through the time we have on every line to change anything at all. So it's incredibly difficult. Now, let's go back to this style wasync, because again, if we change it, it behaves very differently. So what's going on here? So WSync is another special kind of register. And when we store something to it, it's called strobing the register. It doesn't actually matter what you put in it. It just tells the system to do something. And WSync in particular, when you strobe that register, it tells the chip to wait until you get back to the start of the line. So essentially what's happening here is when we get to next frame here, we take a color, we change it, then we wait until it moves to the next line, and keep doing that and keep doing that and then jump around. So the reason this makes a difference is with it when it's not there, like I said, it's actually changing the color in the middle of drawing the line.
1/3 of
so
US
the color
bandwidth
changes.
is used by Netflix.
When I pull it here,
the rest
now
is
it's
used by
but here's the thing again.
Node_modules
Why is it
and NPM
doing this weird kind of
install.
strobe? And this is because we're not synchronizing this action. Every line it draws is changing the color. But if you look at this, you can see pretty clearly, remember I said this is a cycle of 256. We have a non-multiple of 256 there. So as it runs through, it's constantly getting out of sync. So let's see what we could do to make that a little better. Let's do a smooth background change.
Yep. So we got another donation in from Programmer's Rule, getting us slightly closer to our goal. We are just a little over, what, $266.40. I think I did that right in my head right now. Away. We're getting so close. So thank you again for those donations. And yeah, the racing the beam stuff is crazy and wild. And, you know, we were talking earlier in the dev panel when we were talking about, you know, the tools that are available now. Strobing the Register just donated $5.
Thank you, Strobing the Register.
And
you can strobe my register any day.
And Racing the Beam was not the canceled sequel to Gleaming the Cube. Gleaming the Cube, it never needed a sequel because it was perfect in every way. But yeah, it's incredibly difficult to think about some of these things. It's totally doable, but you have, like, as Matt was kind of saying, beyond understanding like programming and logic and how do you kind of put things into different places in memory and use assembly, you also need to understand the tech completely, like inside and out. You need to understand the console, you need to understand the TV that the console is going to output to, and how all of it works together to basically make changes live in the code such that when the electron beam catches up to that spot, it does the thing that you want it to do, which is wild.
Well, and the people who were originally writing these cartridges, they didn't have a real-time system like this. They were using separate computers that built to dev kits essentially. So let's just quickly, let's try and make this work better. So I'll go through some of this other crap here in a second, but now we're going to do this. So we have DEY, STY, call a bouquet, and sta wasync. Okay.
Just a, you know, strobing lights warning, so a lot of people know.
It's extremely stroby. I will
might want to tone that down when we're not needing it. Oh, and Arsenio shows up with $5.
Thank you, Arsenio.
20,000, let's go.
20,000, let's go. We're almost, yeah, we're...
Okay. So this change doesn't look that different. In fact, you can probably infer DEY, much like DEX, decrements the Y register. So that doesn't look that different. So what's going on here? Why is it nicely synchronized? So basically what's happening here is, if we look at this up here, basically we do this thing that says stop vsync wasync. So going back to our scanline thing, we have this vertical sync here. So first of all, we're now telling it correctly. We're telling the TV to do the vertical sync correctly. This here is a loop. Now loops are pretty common in programming, but in assembly language, one of the odd things is you can't just like loop until something is equal to something else. Instead, what you have is these various instructions that branch when something is 0 or not 0. But in this case, we put 37 in a loop. We loop through. So this basically does 37 vertical lines, weighting each line. So now that gets us to our blank area here. So now here's our code. So we change the color, and here's the other key thing. Now we weight 192 lines and then 30 lines. So the reason that this looks better is because we're now correctly synced with the scan lines. Fooch, you want me to keep going? Let me know when you want me to stop.
I think you're good right now. I think maybe if you, I don't want to like put you out, but also potentially accelerate to like some of your deeper, like I think you laid solid foundation, but maybe jump to like chapter 7. You know what I mean?
Absolutely. So let's jump to, we're going to jump all the way to sprites. Now, for those of you that are familiar with game development or, you know, TV or whatever, you know what sprites are. They're things you can draw on the screen. And somewhat amazingly, one of the things that the 2600 can do is draw sprites on the screen. In fact, it can draw up to 2 sprites. So let's draw that sprite here. So I'm going to go here and I'm going to type load a 32. And I didn't mention this earlier, but so a £sign means this is a number, not the address of something. And the $sign means treat this as hexadecimal. So now I'm going to store it in this new thing called callup0. Then I'm going to load AA and store in grup0. Oh, and look at that. So let's talk about sprites in the 2600. A 2600 sprite is exactly 8 bits wide. It has no height. It is only one line. So you can draw a sprite, but it's only 8 bits wide, and you can see that what's happening here is essentially the way sprite drawing works, is when you turn on a sprite, it just keeps drawing it in perpetuity until you turn it off. Now, let's see how we can make this a little more interesting. So now I'm going to load 0 in block 2. All right, now this looks a little better because what we've done is draw the sprite, wait 10 lines, then undraw the sprite. So when we say draw a sprite, really all that it means is you turn on or turn off sprite drawing. And then what we can also do is time where it is horizontally by changing this number here. But if we look at this, one of the weird things that's going to happen is, you see how it's moving in big chunks? That's because there's no way when you draw a sprite, you don't say put it at the screen at this line and location. No. You only turn it on and off. And if you want it to appear later on the line, you just have to time it. So the reason that as I go 1, 2, 3 here, it doesn't change, That's because for that period of time, I'm still in the horizontal blank. It's not changing anything. It's just not drawing. Once I get to 4, 5, 6, now I can move it more. There's some like magic you can do to fine tune it, but that's how confusing it is. Also, if we go back,
sorry,
go
I
ahead.
just wanted to like jump in on that because I do love just like that concept of like, in case it was, just to push it forward, is like, you don't pick like an XY on the screen. You don't pick like a location in a 3D, editor. You don't put something at a location and any of that. You say something that's moving at like the speed of light. Where will it be at this point in time, and draw it right now to pick where it's going to be. And like, so it's you're actually using time to draw something as you're timing out where the electron beam will be at the point where it starts drawing it, as opposed to just placing it in a spot. It's an insane way to think.
What's really happening here, if you look, is in this part of my code, we're still in the vertical blank time, which is basically your main loop time. And the resp0 register, when you strobe that, it will lock in the sprite at your point in the clock. Remember, we have these clocks, so it's going like this. So by changing this number, all I'm doing is changing this loop to adjust the point at which I strobe that register and set it. Okay, but this is actually the last exercise in the first segment of this, because the original idea here was that we could draw the Buffalo Game Space logo, which you can see on the Twitch page with that beautiful controller and Buffalo and whatnot. But that proved kind of complicated, so we're gonna still do a multi-line sprite and see how that works. Okay, so let's scroll down here. So what I'm going to do is load a button frame 0x star a group 0. Load a buttons color frame 0x star up call up 0. Buttons frame. Okay, and whoa, look at that. We have a sprite which is as close as I could come to our actual logo by just saying, okay, those are the 4 buttons. Okay, so we can do a multi-line sprite. So how's that working? Well, okay, so we already know what what star group 0 does, which is set the code for the data for a sprite. And call up 0, you can figure too, this sets the color for a sprite. So, but you see this new format here called comma X. So when we just say LDA button frame 0, this is saying take the data at the address button frame 0 and put it in the accumulator. If we say LDA button frame 0 comma X, this is saying take the accumulator, take the value at this address plus the value of X and load that. So how does that work? So essentially we have this X, so we loop through 8 lines of X. And if we scroll down here, now we see the raw data in our virtual ROM that represent the lines and the colors of the control. Whoops, that is my cat being a jerk.
Is everything okay?
No, the cat likes to climb on the screen.
That was awesome. I thought you fell over for a second there. Okay.
I have no idea what it looked like. Oh, yeah.
Well, it's because you have your background, so it's like the pitfall is just like boom, and you just like fell into pitfall for a second.
Oh, that's funny. Yep. I fell in the pitfall. I'll answer that timing question in a second. But if you look here very carefully, you can see that these ones kind of correspond to the shape of this. And when I said earlier hexadecimal is useful, it's partially because you can turn these, a lot of times you're just literally writing the sprite. So now this is a case where you don't have to do it by hand because there are some tools online like this one where if you want to make a sprite, let's make a sprite here. Let's make a terrible smiley face. We can do something like that. And then this will actually generate, the data you need. So this is what a sprite editor looks like for the Atari. But again, when we're talking a multi-line sprite in the 2600, you're literally just turning things on and off. And remember, there's only 2 sprites. So when you start to think of a game like Pac-Man and how many things are on the screen, basically getting to the point of being able to do something like that is, for all practical purposes, magic. And sort of getting to the end of this section, let's think of some of the other kinds of things we might do on a game. So random numbers, you do it yourself. Saving games, I mean, there's no place to save them. There's literally no input output other than the screen and controllers. Drawing shapes, absolutely nothing. Text, good luck. Floating point math, I mean, you can't even do 16 bits. Like, the only math it can do is from 0 to 256 by default. Ray tracing, I said lol, you can actually find people who've managed to make ray tracing things on the 2600.
I mean, if you want to be pedantic, it's all ray tracing, right?
Well, okay, ray trace 3D objects. And, so in this little exercise here, and I'll come back to a couple of questions, but just so you've learned some 6502 assembly, you've learned load A, load Y, load X, store A, store Y, store X. I didn't show these, but TAY, TAX, transfer the accumulator to Y or X. You learned DEX, you learned branch, you learned a bunch of 2600 registers. And even beyond 2600, with the stuff you've learned here, like, if you're interested in this stuff, what are some of the things you can do? You can make 2600 games.
Let's
you can make
get
games
that
for
20K.
2400 or 800.
Do it. Let
you can make NES games. You can make
FRAGGING.
Apple II games. You can make games for the C64 or PET or VIC-20. You can make Atari Lynx games. Or you can start with this and learn x86 assembly if you wanted to. I'll also note that there are some tools that essentially compile a language to assembly, so you can do some easier things, but you really have to understand how the system works to get anywhere. And let's see, there was a question about timing.
So while you're picking that up,
go ahead.
That we just got another donation from the Buffalo FGC, getting hype going and going for that 20K. Let's go. We're under $250 from the goal. We're within striking distance. Thank you, everybody, for all the support all day. It's been a long day, long set of streams, lots of really cool things. And thank you. We're almost there. Thank you all so much. We're going to get there. Okay, and Matt, get back to question.
Yeah, guessing the timing. I mean, so you sort of, like, you have the screen chart, and you have, when you're using a tool like this, you have it tells you the timings here. If I'm really developing something, so like this is a game I'm working on, which is a rhythm game. But when you
assembly rhythm game, you're a madman.
Yeah, it's kind of nuts. But when you use Stella, which is this emulator, you have an entire set of debugging tools where you can go in and look where things are and what you need to do. But honestly, you kind of spend a lot of time just fiddling with things to get them to work. There's really no way around that. And just maintaining things in your head. I think probably the biggest challenge is because you have so little resources, and like this makes it seem way better than it is. Honestly, it's just so much worse than this because you run out of stuff so fast. Because even an extremely simple loop, I want to loop through 36 lines, say, that takes almost 10 cycles. And 10 cycles, again, is half of the time you have on a line before it starts drawing anything at all. So you'll just build something, and then it becomes it just becomes this. You just have to completely redo it and figure it out.
Sword Moss representing the 585. Appreciate the donation.
Thank you, Sword Moss. And so it's just a really interesting challenge. And I had a bit earlier in the deck. It's basically, I think part of what's interesting about working with these kind of constraints is, most of the time when you're making a game, you have an idea for a game and then you just kind of implement it. Here, the system itself controls so much of how it works. Like if you look at my screen back there, the reason Pitfall looks the way it does is essentially because of how the 2600 works. In fact, I didn't really cover this too much, but when you look at like these blue bars on the side, there's a thing called the play field, which are some additional registers you can flip to draw things. And a lot of the blocky linear nature of this is because what people figured out was that you could use those registers to draw things or do timing. And like if you look at like Pac-Man or something, like the Pac-Man version for the 2600 is notoriously terrible and has flicker all over the place. It has flicker because you again have to do magic to get more than two sprites on a line at once. Essentially the way to think about it is that the 2600 was made to make the game Pong. That was it. They just wanted a way to make Pong and Pong-like games, and everything else that people managed to do was essentially magic. The only other thing I would say here is that if you kind of enjoyed the challenge of the 2600 programming, there are some non-2600 games that are pretty great. You can play them on Steam. Specifically, you've got TS100, Shenzhen.io, and Exapunks by a developer called Zachtronics. They all are based on a 6502-ish fake assembly language with a series of puzzles, and it's actually a really good way to get up to speed with how these things work, because you're also in these games are constantly optimizing your timing and cycle count and stuff like that. I think the final point, because you might be like, well, why are you doing this at all? I mean, some of it is kind of nostalgia, but I think a lot of it is just because it's just a really interesting challenge. And what's neat about building for a system like this, or even something like the NES, is when you build a modern game with something like Unity, the amount of stuff that's going on is essentially incomprehensible. Like, you understand how things work abstractly, but it's very hard to really understand every part of the stack. What's neat about programming in this era is understanding the CPU and the system as a machine, like a clock. And you can understand how it works extremely accurately and have it mapped out in your head. And you can't even get it to do anything that you want unless you understand it with that level of pure clock-like accuracy. And so it's satisfying in an intricate way that you just don't get with modern systems. So I think I'll leave it there. Futch, I don't know if anyone has any other questions.
There was a bunch of interesting questions, but the main thing, I think you covered all of them, but the other one was just like, yeah, no music, right?
Well,
I mean, you can kind of time out some blips and bloops if you get real creative.
No, it's the 2600, so it's weirder than that. You have two voices, and you can have multiple effects and volumes, and it works for registers, so you can stick things in there and they play. So it's not like the Apple II where it's literally a speaker you can beep on and off. However, the way the sound chip works, again, to save money, it's not a major or minor or chromatic scale. It's just some other mathematical things. So the notes don't actually match up to scales. So it's really, really hard to get anything that sounds good out of it. So again, it can do sound and it's okay. Again, you can have two voice sound, but it's complicated, and you run back into the time problem. There's actually a library that someone wrote that I used for that. rhythm game where you can kind of write your music, and there are some tools for writing it. But again, it's not like normal chiptunes, because you can't just have something that's like, C, E, G, E, C. It's just, it's just note 5, note 10, note 15, and they aren't necessarily sounding great together.
Yeah, some crazy stuff. All right. So, with this, I'm going to pop this back out, and we're just going to go to a desktop for right now. Move this over here so everybody doesn't see our chats.
Oh, and I'll add, like if anyone's interested in this stuff, feel free to join BGS, join our Discord, talk with us further. There are people who do other, there's a guy who likes ColecoVision stuff. In fact, I think he can't be here because he's at a ColecoVision virtual conference or something. So there's a lot of people with interest in classic games and emulators and stuff like this.